Hello, everyone. Tonight we are diving deep way back into a time when giants truly roamed the earth. Imagine standing in a vast open grassland, the air cool and carrying the scent of damp earth and unfamiliar vegetation. Towering before you isn't a skyscraper, nor a familiar elephant from a zoo, but something else. A creature of impossible scale, a shaggy mountain of fur and muscle, its silhouette breaking the horizon line like a forgotten monument. This is the world of the Megatherium, the giant ground sloth. And frankly, if you were suddenly dropped into its Pleistocene domain in your pajamas, you probably won't survive this. The sheer indifference of nature on that scale is a swift and efficient editor of unprepared visitors. So before you get comfortable, take a moment to like the video and subscribe, but only if you really enjoy what I do here. And hey, while you're at it, drop your location and local time in the comments below. It's always fascinating to see where everyone is tuning in from as we explore these lost worlds. I see folks from Buenos Aires already quite fitting for tonight's star. Midnight in Berlin, hello? And someone from right around the corner, comparatively speaking in California, where cousins of our great beast once roamed. Now turn off the lights, maybe turn on the fan for some soothing noise, and let's embark on tonight's journey together. You find yourself shuffling along, not on familiar pavement, but through coarse, knee-high grasses that whip against your legs, leaving tiny, itchy trails. The air is crisp, carrying a dampness that hints at recent rain, or perhaps just the permanent exhalation of a land teeming with life and punctuated by sprawling wetlands. It's a world painted in muted greens and browns under a sky that seems wider bluer than any you've known. The light has that peculiar clarity of pre-industrial times where every distant ridge stands out in sharp relief. You're small here, inconsequential, a feeling modern life rarely affords us, preoccupied as we are with our notifications and our meticulously curated digital selves. Here the only notification is the rustle in the undergrowth, a sound that could mean anything or nothing. Then the ground beneath your feet, which you assumed was solid, gives a subtle, almost imperceptible shudder. Not an earthquake, more like the world taking a heavy breath. You freeze, every sense dialed up to 11, your heart doing a frantic little tap dance against your ribs. Another shudder, this one a bit more pronounced, accompanied by a sound like a giant bellows, a slow, whooshing exhalation that seems to come from everywhere and nowhere at once. You scan the horizon, a line of low rolling hills fringed with dark coniferous-looking trees that are definitely not your local pine. And then you see it, or rather, him or her. It's hard to tell from this distance, and frankly, gender politics are the last thing on your mind when confronted by something that redefines big. Emerging from a copse of those unfamiliar trees, moving with a ponderous, deliberate slowness that nonetheless covers ground with surprising efficiency, is Megatherium. The great beast, the name you'd later learn if you somehow survived to Google it, means exactly that. And for once, scientific nomenclature didn't undersell it. It's like calling a blue whale rather large fish-shaped mammal. Accurate, but it misses the poetry of sheer overwhelming presence. It stands for a moment on its massive hind legs and thick tail, forming a tripod of such stability it could probably withstand a hurricane, or at least a very enthusiastic Labrador. In this stance, it easily reaches 20 feet into the air, its great shaggy head surprisingly small for such a colossal frame. Browse leisurely on the high branches of a tree you hadn't even properly registered as being tall. The leaves, which moments ago seemed like an undifferentiated mass of green, are now clearly individual morsels plucked with an almost delicate air by a long, prehensile tongue, or perhaps pulled in by those enormous, curving claws. Claws that even from this distance look less like fingernails and more like a set of agricultural implements designed by a committee of very angry bears. You remember reading something, a fleeting image, from a half-forgotten documentary about how these creatures were initially pieced together by scientists who were utterly baffled. The first nearly complete skeleton of Megatherium americanum was unearthed in Argentina near the Luján River and sent to Madrid in 1789. It wasn't until 1796 that the legendary Georges Cuvier, the father of paleontology, some might say, studied the drawings and correctly identified it as a gigantic extinct relative of modern tree sloths. Before that, You can only imagine the wild theories. Some monstrous ape, perhaps, or a creature that defied all known categories. Cuvier himself initially thought its massive claws were for digging up roots, a theory that persisted for some time. The beast before you drops back to all fours with a sigh that ruffles the distant leaves and a thud that you feel more in your bones than hear with your ears. Its fur is a matted, shaggy affair, probably a rich, earthy brown, though it's hard to tell with a layer of dust and dried mud caking its flanks. It's the kind of coat that looks like it could hide a small family of birds, or perhaps several very large, very content parasites. You ponder for a wild second what something that size would smell like up close. Probably not great. Think of a wet dog, but a dog that's the size of a small bus and hasn't had a bath since the early Pleistocene. The sheer volume of plant matter it must consume daily would also lead to, shall we say, rather significant organic deposits. It's a quirky thought, but paleontologists have found fossilized sloth dung or coprolites from its relatives, some the size of melons, giving us direct insight into their plant-based meals. You can only imagine the scale for Megatherium. You'd need a serious pooper scooper for that situation. It moves with a slow, swaying gait, each step deliberate, its immense weight pressing deep into the soft earth. There's an undeniable power in its movements, a sense of ancient strength that makes the hairs on the back of your neck stand up. Yet there's no malice in its demeanor, no predatory gleam in its distant eye. It seems entirely preoccupied with the business of being a megatherium, which as far as you can tell mostly involves eating existing and being very, very large. Paleontologists still debate just how much time these giants spent on their hind legs versus all fours. Was it primarily for reaching high foliage as you've just witnessed, or did it also serve a purpose in defense, or perhaps even in locomotion over certain terrains? The sheer robusticity of its pelvis and hind limbs suggests bipedal posture was fairly common. But like so much about these animals, the exact details are shrouded in the mists of time and ongoing research. You watch it amble towards a large flat rock perhaps to bask in the pale sunlight that's now breaking through the morning haze, or maybe just because that particular rock owed it money. It's hard to say. What is clear is that this creature, this gentle giant, is perfectly attuned to its world, a world of vast open spaces of mega-herbivores and the predators that inevitably followed them. Its very existence is a testament to a time when the rules were different, when size was a viable evolutionary strategy, and when the Earth supported life on a scale that dwarfs our modern sensibilities. And as you stand there, a tiny, anachronistic speck in this ancient land, you realize that understanding this creature, its life, its diet, its eventual disappearance, is to understand a crucial chapter in the story of life itself. Its bones hold secrets. Its teeth whisper tales of meals consumed tens of thousands of years ago. The real journey is just beginning. That immense creature, your Megatherium, eventually settles onto its chosen rock, the very earth seeming to sigh in relief around it. And as you watch hidden in the rustling Pleistocene grasses, your mind understandably starts to churn. How did we even begin to understand such an animal? It's not like they left behind instruction manuals or neatly labeled museum exhibits in their wake. No, our knowledge is a painstakingly assembled mosaic built from fragments of bone teeth and the occasional incredibly lucky fossilized dropping. It began as these things often do with someone stumbling upon something they couldn't quite explain. Picture this, it's 1788, a good while before your current, rather precarious jaunt through time. You're not in these grasslands, but on the dusty plains of what will one day be Argentina near the Luján River. A friar, one Manuel de Torres, is going about his business when he or someone in his party comes across a collection of truly enormous bones eroding out of a riverbank. Not just a few fragments, but a significant portion of a skeleton. Now people had probably been finding bits and pieces of these giant creatures for centuries, maybe weaving them into local legends of bygone monsters or titans. But this was different. This was a find that would make its way into the formal corridors of science, or what passed for it in the late 18th century. This particular discovery, the first reasonably complete skeleton of Megatherium americanum to be scientifically documented, was carefully excavated. Think about the sheer labor of that under the Argentinian sun, with 18th century tools carefully extracting bones that weighed more than the excavators themselves. It's a legitimate historical event that truly kicked off the scientific journey with this animal. These bones were packed up, and you can imagine the logistics of shipping something like that across the Atlantic back then, no bubble wrap or FedEx priority overnight, and sent all the way to the Royal Cabinet of Natural History in Madrid, Spain. There in Madrid, the bones caused quite a stir. Remember, this is a time when the concept of extinction was still a bit wobbly. Many learned folks influenced by the idea of a perfect unchanging creation struggled with the notion that entire species could simply vanish. And even if they accepted extinction, what was this thing? The bones were assembled or perhaps wrestled into a plausible shape might be a better description by Juan Bautista Bru, a museum employee and artist. Bru also drew the skeleton, and it was these drawings that eventually made their way to Georges Cuvier in Paris, the man you briefly met in your thoughts earlier. He was the one who, with his deep knowledge of comparative anatomy, finally put a name and a family to the beast, recognizing it as a giant extinct ground sloth. But before Cuvier's clarifying insights, imagine the scene in Madrid. Scholars, naturalists, and probably a few bewildered aristocrats staring at this skeletal behemoth. What wild ideas must have danced in their heads? The bones were so large, some might have whispered of giant humans from a biblical past. Imagine the size of its shoes. You might quip to yourself, though they probably weren't wearing shoes. Others trying to fit it into known animal groups would have been utterly stumped. It was like trying to assemble a piece of IKEA furniture with instructions written for a completely different, possibly alien product line. Sure, this bit looks like it should connect here, but then this other part is clearly from a coffee maker. The sheer size of the claws, those magnificent, terrifying scythes you saw earlier, must have been a particular point of contention. What were they for? Some early theories, even after it was identified as a sloth relative, suggested they were for digging colossal burrows. You picture Megatherium as a sort of oversized shaggy badger excavating subterranean palaces. It's a charming image, but the energy expenditure would have been significant. Others perhaps getting a bit carried away with the sloth connection and looking at its powerful limbs might have posited it climbed trees. Now, modern tree sloths are arboreal, yes, but they're about the size of a well-fed house cat. Megatherium weighed several tons. The kind of tree that could support it would need a trunk wider than your living room, and its ascent would have been less of a climb and more of a slow-motion demolition. The squirrels must have been absolutely petrified, assuming they weren't already part of the structural damage. And here's a quirky little fact for you, Jose Garriga, who took over the task of mounting the original Madrid skeleton after Bru initially had it in a very low, almost crawling posture with its knuckles on the ground. Some even say a bit like a giant mole rat preparing to dig, or perhaps a creature adapted for swimming. It shows how difficult it was to interpret the biomechanics of an animal so unlike anything alive today. Paleontologists still debate the exact details of how these early skeletons were first assembled and the degree to which preconceptions might have influenced those initial reconstructions. For instance, there's discussion about whether all the bones found by tourists truly belong to a single individual, or if given the context of a riverbank deposit, which can accumulate remains from various sources over time, it was a slightly more composite picture from the get-go. The very notion that this creature so robust, so clearly powerful, was related to the small, famously lethargic tree sloths of South America must have seemed almost preposterous to some. It required a leap of anatomical insight, a faith in the patterns of comparative biology that Cuvier championed. He saw past the incredible size to the underlying skeletal structures, the shape of the teeth, the construction of the limbs, the peculiar articulations of the vertebrae. That clearly linked Megatherium to the Xenarthrans, that unique group of South American mammals that includes sloths, armadillos, and anteaters. So as you continue your rather surreal observation of this living, breathing Megatherium munching away on leaves high above, you can appreciate the journey of understanding that brought us even this far. From those first dusty bones pulled from a riverbank sparking confusion and wild speculation, to the meticulous studies that slowly, piece by piece, revealed the nature of this Ice Age titan. It's a testament to human curiosity, our innate desire to make sense of the world, even a world that has long since vanished. The initial wild ideas, the missteps, the debates, they're all part of that wonderfully messy, utterly human process we call science. And it's a process that continues today as we keep unearthing new clues and refining our picture of creatures like your rather large, shaggy companion over there, who seems to have just dislodged a small bird's nest entirely by accident, of course. The bird, a tiny flash of iridescent blue, is now chattering indignantly from a nearby branch, thoroughly unimpressed by prehistoric majesty. That indignant little blue bird, now thoroughly flustered, finally zips away into the deeper green of the forest, leaving your Megatherium to its rock basking or whatever profound existential pondering it's currently engaged in. It's a moment of surprising, almost comical calm after the initial shock of its appearance. And it's in these quiet moments of observation, much like those early scientists poring over dusty bones in dimly lit European museums, that the first coherent picture of this animal's life began to take shape. Once the initial, what on earth is this thing phase passed, and Cuvier had pointed them in the general direction of giant sloth, the next big question was naturally, what did it eat? You can't be the size of a double-decker bus or perhaps a very generously proportioned food truck without a fairly substantial grocery bill. For a very long time, the answer seemed obvious, almost self-evident: plants. Lots and lots of plants. You're now firmly stepping into the era of the great plant-eater assumption, a comfortable, widely accepted theory that painted Megatherium as a dedicated, if rather oversized, vegetarian. This wasn't just a wild guess mine, you not like some of those early climbs giant trees flights of fancy. This was an idea rooted in the emerging science of comparative anatomy, championed by the very same Georges Cuvier who first classified it. He looked at the teeth, those strange peg-like structures, and saw not the shearing blades of a carnivore, nor the complex grinding mills of a modern cow, but something he and others interpreted as perfectly suited for crushing and grinding tough vegetation. Imagine those early paleontologists, their frock coats probably dusted with bone meal, carefully examining the jaws. They'd note the lack of sharp tearing canines, the absence of slicing carnassials that you'd find in any self-respecting meat eater. Instead, they saw these robust, continuously growing cheek teeth. That continuous growth is a neat trick, by the way, common in animals that eat abrasive foods. As the tooth wears down, more tooth erupts to replace it. Handy. Imagine the dental bills if they had to see an orthodontist with that setup. You muse watching your specimen idly scratch its massive flank with a claw that could probably detail a car or remove its engine. The teeth, they reasoned, were designed for a life of relentless munching on branches, leaves, and perhaps even roots. This herbivorous image was further solidified by the sheer bulk of the animal. Creatures that large in the common understanding of the time, and largely still today, tend to be plant eaters. Think elephants, rhinos, hippos, all colossal vegetarians. The energy pyramid with plants at its broad base can simply support more large herbivores than it can large carnivores. Plus its presumed slowness, a characteristic inferred from its massive build, and the famously leisurely pace of its modern tree-dwelling cousins didn't exactly scream apex predator. It all painted a picture of a slow-moving, peaceful giant, a sort of prehistoric lawnmower on a truly epic scale. It probably considered an entire forest a light snack. You chuckle softly, careful not to attract its attention or that of anything else that might consider you a light snack. The renowned British paleontologist Sir Richard Owen, a towering figure in 19th century science, and a man whose relationship with Charles Darwin was, let's just say, complex, did much to popularize and detail this herbivorous view. Throughout the 1840s, 50s, and 60s, Owen published extensive monographs on Megatherium, meticulously describing its anatomy and reconstructing its lifestyle. This was a legitimate historical event in the study of Megatherium, as Owen's work became the standard reference for decades. He envisioned it rearing up on its powerful hind legs and tail, using its massive arms and claws, not for unearthing lost pirate treasure, but for grasping tree trunks and pulling down heavy branches to bring choice leaves within reach of its mouth. He even suggested it had a long, prehensile tongue, much like a giraffe's, to further aid in stripping foliage. Of course, even within this generally accepted herbivorous framework, there was plenty for the academics to chew on, so to speak. Paleontologists still debate even now the specifics of its plant-based diet. Was it a high browser focusing on tree leaves like Owen suggested? Or did it also consume tougher vegetation? Perhaps even digging for roots and tubers with those formidable claws. The wear patterns on its teeth and the biomechanics of its jaw would later offer more clues, but in those early days it was a topic of lively discussion. Some early, rather dramatic illustrations even depicted Megatherium uprooting entire mature trees just to get at the topmost leaves. A bit like using a bulldozer to pick a daisy, but an undeniably effective, if somewhat theatrical approach to salad acquisition. It's a quirky fact that these almost King Kong versus the Triffids style depictions really captured the public imagination, emphasizing the creature's power even as a plant eater. The peaceful giant narrative was compelling. It fit a certain archetype, a vision of the prehistoric world where not every enormous creature was a ravening monster. There was something almost noble about this colossal vegetarian peacefully munching its way through the Pleistocene. It was an image that would persist for well over a century, deeply embedded in textbooks, museum displays, and the popular consciousness. And why not the evidence, particularly from the teeth and the general body plan, seemed to point squarely in that direction. The idea of Megatherium as anything but an herbivore would have seemed to most scholars of the 19th and early 20th centuries as outlandish as suggesting that cows secretly yearn for a steak dinner. So as you're observed, Megatherium lets out another ground-trembling sigh and perhaps shifts its 20-ton bulk a few inches on its sun-warmed rock. You can see how this gentle giant persona took root. It was built on solid anatomical observation, supported by leading scientific figures, and it just made sense. The case for herbivory seemed strong, almost unshakable. And a huge part of that perceived strength, the real bedrock of the argument, lay in those peculiar, ever-growing, enamel-banded teeth, the very tools of its supposed trade. They held the key, or so everyone thought, to understanding what fueled this incredible prehistoric engine. Your colossal companion on the rock lets out a sound that's halfway between a sigh and the rumble of distant thunder, its massive rib cage expanding and contracting like a blacksmith's bellows. Perhaps it's dreaming of endless, leafy buffets. And as you continue your vigil, your thoughts drift back to those remarkable teeth, the ones that for so long defined Megatherium as the ultimate prehistoric vegetarian. It's one thing to say, oh, it ate plants because its teeth look like herbivore teeth. It's another to truly appreciate what made them such compelling, if somewhat peculiar, evidence. Imagine, if you will, that you could get a close-up look. A very, very safe close-up look, perhaps with a high-powered pair of imaginary binoculars. You wouldn't see a gleaming row of incisors at the front, no sharp canines for tearing. Megatherium, you see, was rather minimalist in its dental fashion at the prow of its mouth. No front teeth at all in Megatherium americanum. Not great for politely nibbling an apple, you think, but then again, apples weren't really on its prehistoric grocery list, and polite probably wasn't a word in its vocabulary either. Its business end, dentally speaking, was all in the cheeks, 5 robust pillar-like teeth on each side of the upper jaw, and 4 on each side of the lower. These weren't your average run-of-the-mill molars. They were more like grinding columns, deeply set and ready for serious work. Each tooth was a marvel of natural engineering, a sort of natural file cabinet for foliage. They were hypselodont, a lovely term that simply means they were ever-growing, erupting continuously from the jaw throughout the animal's life. This is a crucial adaptation for any creature munching on tough, abrasive plant material day in and day out. Plants, especially grasses or those carrying a lot of grit from the soil, can wear down teeth at an alarming rate. So if your teeth don't keep growing, you quickly end up with a gummy smile and a very empty stomach. It basically had its own built-in tooth regeneration system, you muse. Wolverine, eat your heart out. Or, well, maybe don't. That sounds messy and counterproductive for a herbivore. The really clever bit, though, was the composition of these teeth. Adult Megatherium teeth, particularly those of Megatherium americanum, lacked the hard outer layer of enamel that you find on your own teeth or those of many other mammals. Instead, they were constructed from layers of different types of dentine, a softer, bone-like material, and cementum, there was often a harder type of dentine forming ridges and softer dentine and cementum filling in the gaps. As the animal chewed, these layers wore down at different rates. The softer parts would wear away more quickly, leaving the harder dentine standing proud as sharp crisscrossing ridges on the grinding surface. It was a self-sharpening system, a bit like some modern industrial grinding tools. Nature's own whetstone. You think constantly keeping those grinders ready for action. No need for a dental hygienist to tell it to sharpen up its act. This differential wear created an incredibly efficient rasping surface, perfect for pulverizing leaves, twigs, and other fibrous plant bits into a digestible pulp. The jaw movement itself was also specialized. The articulation allowed for not just an up and down crushing motion, but also a good degree of fore and aft and side-to-side grinding, further enhancing their ability to process plant matter. You can almost hear it in your mind, a rhythmic, powerful crunch, grind, the soundtrack to a Megatherium's lunch break, which probably lasted most of the day. This intricate dental machinery was meticulously studied by paleontologists throughout the 19th century. After Cuvier and Owen laid the groundwork, others continued to build upon it. For instance, the German-Argentine paleontologist Hermann Burmeister, who spent many years working in South America from the 1850s onwards, produced incredibly detailed studies and illustrations of Megatherium and other South American megafauna. His work, a significant historical event in South American paleontology, further cemented the image of Megatherium as a highly specialized herbivore, perfectly equipped by its dentition to thrive on the continent's vegetation. He painstakingly documented the structure of these teeth, comparing them to other known herbivores and reinforcing the consensus. It's a quirky thought, but given their ever-growing nature, if a Megatherium somehow found itself on a diet of exceptionally soft, non-abrasive food, for an extended period its teeth could have, in theory, overgrown. Imagine the discomfort, a prehistoric toothache of epic proportions requiring perhaps a very brave, very well-insured dental surgeon with a rock hammer. Or maybe, as you jest to yourself, it'd need a Dremel tool for a tooth trim every few months, strictly off-label use, of course. Even with this strong dental evidence for herbivory, paleontologists still debate the precise nature of the vegetation these teeth were best suited for. Were they optimized for stripping soft leaves from branches, as Owen suggested? Or could they handle much tougher, more fibrous materials like coarse grasses, woody stems, or even silica-rich plants that would be incredibly abrasive? The exact toughness and type of coarse vegetation it consumed remains a topic of ongoing discussion, with different researchers emphasizing different aspects of its dental toolkit and wear patterns. But for well over a century, the story told by these teeth was clear and compelling. Megatherium was a plant eater through and through. Its mouth was a highly efficient, self-maintaining processing plant for vegetation. The case seemed closed, the evidence literally etched in dentine and cementum. You look at the distant, placid bulk of the creature before you, and it's easy to see why this interpretation was so enduring. It looks like a giant, shaggy, mobile compost heap in the making. Its whole demeanor screams, "Pass the salad." Yet, as with any good detective story, especially one pieced together from clues millions of years old, focusing on just one piece of evidence, however convincing, can sometimes mean you miss other, more subtle parts of the picture. Teeth are vital, no doubt, but a creature is more than just its mouth. It also has claws, limbs, a body built for, well, that was becoming the next big question. The Megatherium before you shifts its immense bulk again, one of its massive forelimbs extending languidly as if to stretch. Your gaze is drawn inevitably to those claws. You saw them earlier, plucking leaves with a surprising, almost out-of-place daintiness for such formidable weapons. But dainty is not the word that springs to mind when you truly contemplate their size and structure. They are not the delicate, needle-sharp talons of a bird of prey, nor the retractable switchblades of a cat. These are more like ivory grappling hooks, thick, powerfully curved, and ending in points that could anchor a small ship, or at least make very serious indentations in whatever they encountered. And it's these very claws, coupled with the incredible power of its forelimbs, that provided another sturdy pillar supporting the grand edifice of the Megatherium as supersized vegetarian theory. Remember Sir Richard Owen, that titan of Victorian paleontology? He didn't just stop at the teeth. He looked at the whole animal, or at least the whole skeleton, and a compelling narrative began to emerge. He saw those enormous claws not as weapons of aggression, but as highly specialized tools for acquiring food. You picture him perhaps in his study at the British Museum, surrounded by casts and drawings, stroking his chin thoughtfully as he envisioned how this creature operated. His idea, which became hugely influential, was that Megatherium would rear up on its massive hind legs and incredibly strong tail, that tripod stance you witnessed, freeing up its powerful forelimbs. Then it would reach out with those arms which were built like hydraulic rams, all thick bones and massive muscle attachment points, and embrace a tree. Not in a loving way, mind you, more like a "you're about to become lunch" kind of embrace. Its gardening technique, you reflect with a wry internal smile, was a less gentle pruning and more enthusiastic arboreal rearrangement. Once it had a good grip, Owen theorized Megatherium would use its sheer strength to pull down entire branches or even topple smaller trees, bringing a cascade of leaves and tender shoots within reach of its relatively small head and that long, dexterous tongue he also proposed. Those claws would act as irresistible hooks digging into the bark, securing its purchase. It's a beautifully simple and rather elegant solution to the problem of being a 20-foot-tall herbivore with a desire for the freshest leaves at the top of the menu. Why bother with a ladder when you can just bring the whole buffet crashing down to your level? It's a bit like someone who, instead of climbing a shelf to get a cookie jar, just pulls the entire kitchen cabinet off the wall. Messy but undeniably effective. And this vision wasn't just confined to dusty academic journals. It was brought to life for the public in a truly spectacular way. In the 1850s, for the Great Exhibition in London, a series of life-size prehistoric animal sculptures were commissioned for the grounds of the Crystal Palace once it was moved to Sydenham. Benjamin Waterhouse Hawkins, a brilliant sculptor, worked under Owen's direct guidance to create these magnificent, if sometimes slightly inaccurate by modern standards, beasts. And there amongst the iguanodons and plesiosaurs was a grand brooding Megatherium, depicted exactly as Owen envisioned, a colossal tree-pulling herbivore. This legitimate historical event, the unveiling of these Crystal Palace dinosaurs in 1854, cemented this image of Megatherium in the public imagination for generations. Millions saw it, marveled at it, and absorbed Owen's interpretation of its lifestyle. It was science communication on a grand, almost theatrical scale. You look at the 4 feet of your observed giant. It's thought that Megatherium and many other ground sloths walked on the sides of their feet, a posture known as pedalateral, or sometimes even on their knuckles, particularly with the 4 feet. This would have helped to keep those enormous claws from becoming blunted or damaged by constant contact with the ground, and it certainly wasn't conducive to chasing down fleet-footed prey. A bit like trying to sneak around in oversized clown shoes, you muse, but for a very serious claw-protective purpose. This specialized way of walking further suggested that the claws were indeed tools reserved for tasks more demanding than simple locomotion. The sheer power housed in those forelimbs is something paleontologists still marvel at. The humerus, the upper arm bone, is short but incredibly broad and thick with huge crests and flanges where massive muscles would have attached. You can almost feel the strain in your own arms just imagining the forces involved. Probably gave the best, albeit potentially bone-crushing hugs in the Pleistocene. You think quickly dismissing the idea of getting close enough for such an embrace. It's this anatomical evidence of immense strength that lent so much credence to the branch-pulling hypothesis. Of course, as with any scientific theory, especially one dealing with an animal no one has ever seen alive, there are always nuances and points of discussion. Paleontologists still debate the exact range of motion of Megatherium's forelimbs. How high could it reach? How dexterous were those clawed hands despite their power? Could it manipulate smaller branches with any precision, or was it all just brute force? And did it target specific types of trees, perhaps those with softer wood or more palatable leaves, or was it an equal opportunity tree molester? The quirky thought strikes you that its manicure routine must have been something to behold, probably involving sharpening those colossal claws on particularly unyielding rock faces or tree trunks, leaving behind gouges that would baffle any future archaeologists not in the know. Imagine trying to use one of those claws to scratch a persistent itch on your back. You ponder. You'd likely end up needing a structural engineer to repair the damage. But despite these finer points of debate, the overall picture presented by the claws and forelimbs as interpreted by Owen and his contemporaries was remarkably consistent with the evidence from the teeth. Here was an animal with grinders for plants and powerful hook-like claws perfectly suited for bringing those plants to the grinders. It all fit together rather neatly, creating a cohesive portrait of a highly specialized high-browse herbivore. It was a lumbering, shaggy giant, yes, but a peaceful one. Its days spent in a slow, methodical quest for foliage. Its most aggressive act being a rather vigorous wrestling match with an uncooperative tree. This image, so strongly supported by two major anatomical systems, was incredibly persuasive. It seemed that the mystery of Megatherium's diet was largely solved. It was a vegetarian case closed. Or was it, as you know, science loves to poke at seemingly closed cases, and the digestive system, that hidden internal world, also had to align with this leafy lifestyle. The Megatherium shifts on its rocky perch, a movement so ponderous it seems to occur in a slightly different time signature to the rest of the world. You notice the immense barrel of its torso, a vast shaggy expanse that must have housed an equally impressive internal landscape. After all, processing the sheer tonnage of leaves and branches suggested by its teeth and branch-hooking claws would require a digestive system of truly heroic proportions. It couldn't just be a simple stomach and a bit of intestine, not for a 20-foot-long, multi-ton eating machine. No, what went on inside that colossal frame was likely a complex, slow-burning furnace, a biological refinery dedicated to extracting every last calorie from its fibrous meals. You imagine its gut not as a delicate series of tubes, but as a vast cavernous network of chambers and passages, a veritable fermentation factory. Large herbivores, especially those dealing with tough plant cellulose, rely on armies of microscopic helpers, bacteria, protozoa, fungi, living in their digestive tracts to break down what they themselves cannot. It had more live-in help digesting its food, you muse, than a Roman emperor had servants, and they probably worked harder too. This microbial workforce would have been essential, toiling away in the warm, dark, anaerobic environment of Megatherium's innards. Paleontologists looking at modern large herbivores and considering Megatherium's unique evolutionary heritage as a xenarthran, that group including modern sloths, anteaters, and armadillos, generally lean towards the idea that it was a hindgut fermenter. This means that the primary fermentation party, where all those helpful microbes did their heavy lifting, probably took place in an enormously enlarged cecum and colon. After the food had passed through the true stomach, think of creatures like horses, rhinos, or elephants. They're all hindgut fermenters. The alternative for gut fermentation is what you see in ruminants, like cows and deer, with their famous multi-chambered stomachs, where food is processed extensively before reaching the small intestine. Given Megatherium wasn't a ruminant, the hindgut model seems the more plausible biological blueprint. This kind of digestive strategy has its pros and cons. It allows an animal to process large volumes of food relatively quickly up front, but extracting all the nutrients takes time. So you can picture the journey of a mouthful of Pleistocene leaves through your Megatherium, plucked, roughly ground by those ever-sharpening cheek teeth, swallowed, and then embarked on a long, slow, meandering tour through its digestive labyrinth. A meal probably took days to make its way through the system, you reflect. Talk about the slow food movement. This was practically stationary food movement, a multi-day spa retreat for foliage. This slow transit time would be crucial for maximizing nutrient absorption from relatively low-quality fodder. The sheer scale of this internal brewery would have been staggering. Its abdomen must have been a warm, gurgling cauldron constantly at work. You might even, if you were brave or foolish enough to get close, hear the faint, deep rumbles and sloshing sounds from within, a testament to the ceaseless biological activity. The warmth radiating from its huge body wouldn't just be from muscle activity. A good portion would be the byproduct of all that fervent fermentation. Of course, a digestive system operating on this scale, breaking down vast quantities of plant matter, would have produced some rather significant byproducts. And here's a quirky little fact for you: the amount of gas, primarily methane, that a herd of Megatherium, if they were indeed herd animals, another point of discussion would have generated, could have been substantial. It wasn't just its footsteps that rumbled, you chuckle to yourself. Its digestive system was probably a one-piece symphony of gurgles and, well, prehistoric flatulence of landscape-altering proportions. One shudders to think of the atmospheric contributions. Probably single-handedly responsible for a noticeable portion of Pleistocene greenhouse gases, its carbon footprint was more like a carbon crater. The detailed understanding of South American megafauna, including the context in which creatures like Megatherium lived and processed their food, owes a great deal to figures like Florentino Ameghino. This prominent Argentine paleontologist working tirelessly in the late 19th and early 20th centuries described countless fossil species and helped to paint a vivid picture of the continent's prehistoric ecosystems. While his theories weren't always correct by modern standards, he famously and rather stubbornly believed that human origins lay in South America. His meticulous, descriptive work and passionate advocacy for Argentine paleontology were a legitimate historical event that laid crucial groundwork. His reconstructions and catalogs of these giant beasts, including ground sloths, implicitly acknowledge the necessity of robust digestive systems adapted to the available flora. Naturally, the precise efficiency of Megatherium's digestive system and the exact configuration of its gut remain topics of some academic debate. Without soft tissue preservation, paleontologists have to infer a lot from the size of the body cavity, the structure of the ribs and pelvis in comparisons with living animals. How effectively could it break down lignin, that super tough component of woody plants? Did it have any unique xenarthran digestive quirks that we haven't even guessed at? These are questions that keep researchers pondering, sifting through the indirect evidence. But for a long time, the general picture was clear: a massive digestive tract, likely a hindgut fermentation system, perfectly designed to slowly and steadily extract nourishment from a diet of leaves, twigs, and other plant materials. It was the internal plumbing that matched the external tools, the teeth built for grinding greens and the claws designed for hooking branches. Everything pointed towards a creature exquisitely adapted to a life of large-scale herbivory. It was another strong piece of the puzzle, fitting snugly alongside the others, reinforcing that image of the peaceful plant-munching giant. Yet inferring a digestive system is one thing. What if you could find more direct evidence? What if you could find, well, the end result of all that digestion? That you realize would be the next rather fragrant step in understanding what truly fueled this magnificent beast. The air around your colossal rock-lounging Megatherium is thick with the scent of damp earth-crushed vegetation from its earlier browse and a certain musky animal aroma that you can't quite place, but it definitely speaks of something very large and very alive. You ponder its inferred digestive system, that vast internal brewery, and the logical next question forms in your mind: if it was processing all those plants, surely it left behind some rather substantial evidence. We're talking, of course, about poop. Fossilized poop, to be precise, the surprisingly informative treasures known to science as coprolites. And yes, you're absolutely right to think that paleontologists, in their unending quest for knowledge, get very excited about ancient droppings. It's a dirty job, but someone's got to do it. For science. You might hear them exclaim, probably while wearing very thick gloves. Gives a whole new meaning to getting to the bottom of things? Coprolites are essentially time capsules from the digestive tract. When animal dung is buried quickly in the right conditions, perhaps in a dry cave or covered by sediment in an anoxic environment, it can over millennia mineralize and turn to stone, perfectly preserving its contents. And what's inside can be a goldmine for understanding diet. You can find undigested plant fragments, leaves, twigs, seeds, pollen grains, even tiny silica structures from plants called phytoliths, all telling a direct story of what an animal was munching on. It's like being a prehistoric food critic, but instead of tasting the meal you're meticulously examining, well, the leftovers. Very, very, very late leftovers. Now, finding a coprolite definitively laid by a Megatherium americanum and directly associated with its skeleton is, shall we say, a bit like finding a winning lottery ticket that also grants you a free pony. Incredibly rare and much debated when claims are made. These giants roamed vast landscapes in their droppings, even if Monumental had to undergo that perfect fossilization process in just the right spot. However, paleontologists have had much better luck with other smaller but still impressively large ground sloths, particularly those that inhabited dry caves in places like the American Southwest. The discovery and study of exceptionally well-preserved coprolites from species like Nothrotheriops shastensis, the Shasta ground sloth found in places like Rampart Cave in Arizona and Pecan Cave in Utah, particularly from the mid-20th century onwards thanks to researchers like Paul S. Martin and his colleagues, was a legitimate historical event that truly illuminated ground sloth diets. These weren't just stony lumps. Some were so well preserved in the arid cave environments that they were more like desiccated dung balls, still retaining much of their original form, and dare one say a faint ancient aroma if you were unlucky or perhaps overly curious. Imagine these scientists carefully collecting these prehistoric meadow muffins, some of which could be the size of a small football, and taking them back to the lab. There, with painstaking care, they would rehydrate them, dissect them under microscopes, and identify the plant species within. The results were unequivocal for these particular sloths. They were browse on a wide variety of desert plants: yucca, agave, mormon, tea, various grasses, and even Joshua tree leaves. It was a direct window into their last meals, a snapshot of their foraging habits. The sheer volume of some of these deposits, layers upon layers of sloth dung, accumulated over centuries in caves, painted a picture of long-term occupation and a consistent plant-based diet. It's a quirky thought, the image of dedicated scientists sifting through ancient excrement with the same enthusiasm others might reserve for gold dust or precious gems. But as they say, one person's trash is another paleontologist's treasure, especially when that trash can tell you what a creature that died out 10,000 years ago had for lunch. The sheer size of some of these ground sloth droppings is also something to consider. If a Megatherium left one of its equivalents on your lawn, you reflect looking at the creature before you. You wouldn't need fertilizer for a decade. You'd probably need a front-end loader and a hazmat suit just in case. While these well-studied coprolites come from other ground sloth species, the findings heavily reinforce the general herbivorous model for the entire ground sloth family, including their largest cousin, Megatherium. If its smaller relatives were dedicated plant eaters, it stood to reason that the giant of the family followed a similar, if much larger-scale dietary path. Of course, paleontologists still debate the specifics when it comes to Megatherium americanum itself. Attributing isolated large coprolites found in South America directly to it can be tricky, as other large herbivores like Gomphotheres, extinct elephant relatives, shared its habitat and might have produced similarly sized contributions. Without direct association with skeletal remains or unique biomarkers, it's often a case of educated guesswork. And coprolites, for all their directness, do have limitations. They primarily tell you about the indigestible or partially digested components. If a Megatherium hypothetically had an occasional meaty snack that was fully digested, it might not leave an obvious trace in its droppings, or the traces might be so subtle they are easily missed or misinterpreted. So while coprolite evidence from its kin overwhelmingly points to a diet of plants, the door isn't completely slammed shut on other possibilities by this line of evidence alone. Still, the image you're building piece by piece is that of an animal whose teeth, claws, inferred gut, and now the dung of its relatives all harmonize to sing a song of herbivory. A very loud, very deep, very rumbly song of herbivory, probably with a lot of bass. The evidence from these fossilized droppings, these direct reports from the prehistoric dinner plate, added a powerful, tangible layer to the story. But even more direct, more intimate than poop would be to find the meal before it became, well before. The thought of those ancient fossilized droppings, those coprolites giving up their leafy secrets, is fascinating enough. It's like reading a discarded shopping list from the Pleistocene. But what if you could get even closer to the source? What if you could find the meal during its journey rather than after its comprehensive processing? You're thinking, of course, about the almost mythical discovery of preserved stomach contents, the holy grail for anyone trying to reconstruct an ancient diet. It's the ultimate peek behind the curtain, a direct look at what an animal was actually putting in its mouth moments or hours before it died. Now, finding such a thing is incredibly astronomically rare. Finding preserved stomach contents, you reflect, is rarer than a politician keeping a promise. Okay, maybe not that rare, but it's certainly up there in the paleontological jackpot stakes. You need a perfect storm of preservation conditions and animal dying in an environment that rapidly desiccates it like a super dry cave or freezes it solid in permafrost like some of those famous woolly mammoths, or perhaps even pickles it in a bog. For a creature as large as Megatherium living in the generally warmer climes of South America, the chances of its stomach contents surviving for tens of thousands of years are slim to vanishing. However, luck has occasionally smiled upon paleontologists studying its smaller but still substantial ground sloth cousins. One of the most remarkable instances involves Nothrotheriops shastensis, the Shasta ground sloth, not your current truly colossal acquaintance, but a notable mega-herbivore in its own right. A particularly significant historical event was the discovery of a mummified Nothrotheriops in a lava tube at Aden Crater, New Mexico, back in the 1920s. This wasn't just bones. This was dried skin hair sinew, and crucially a preserved mass of plant material within its abdominal cavity, its last meal still relatively intact. Scientists carefully collected these remains, and subsequent analysis involving meticulous sorting and microscopic identification of plant fragments revealed a diet rich in desert plants like Mormon tea, globe mallow, yucca, and various grasses. It was like the sloth had conveniently packed a botanical sample kit for future researchers. You really get to know an animal on a personal level. You muse when you're sifting through its final salad course tens of thousands of years after the fact. Similar finds, though perhaps not always as perfectly preserved in terms of stomach contents, have occurred with other ground sloths. For instance, the caves of Ultima Esperanza in Patagonia, Chile, yielded remarkably well-preserved remains of Mylodon darwini in the late 19th century. Explorers like Ramon Lista and later researchers such as Florentino Ameghino and Sir Arthur Smith Woodward were astonished by pieces of skin with embedded bony ossicles and large quantities of dung, all preserved in the cold, dry cave environment. While direct stomach contents from Mylodon are less clear-cut than the Aden crater Nothrotheriops, the associated dung and the overall preservation context strongly pointed to a herbivorous diet. These Patagonian finds, in fact, briefly led to speculation that some ground sloths might still be alive hidden in unexplored regions, a testament to how fresh some of the remains appeared. The analysis of such preserved gut contents is a delicate, fascinating process. You can imagine the scene: a lab quiet, except for the gentle hum of equipment, a paleontologist hunched over a tray of what looks like very old, very dry potpourri, carefully teasing apart plant fibers with fine forceps, identifying seeds under a microscope, perhaps even analyzing ancient pollen grains trapped within the mass. It's like forensic botany, but the victim is an entire species, and the evidence is its last supper. It's like the ultimate prehistoric "what's in your fridge" challenge, you think, except the fridge is a mummified sloth, and the food is 10,000 years old and probably wouldn't get great Yelp reviews. Of course, even this incredibly direct evidence isn't without its interpretive challenges. Paleontologists still debate, for example, how representative a single last meal is of an animal's typical diet throughout its life or across different seasons. Was it eating its favorite food or just what was available in its final hours? Could some plant material have been ingested accidentally while consuming something else? These are the kinds of questions that keep the scientific conversation lively. And it's a quirky, if slightly macabre, thought that when you find perfectly preserved stomach contents, you've essentially stumbled upon an animal's very last interrupted meal. Talk about a meal to die for. You can't help but think, or more accurately, die with. For Megatherium americanum, itself that magnificent beast currently sunning itself like a furry 20-ton boulder, before your very eyes, definitive, universally accepted stomach contents remain elusive. Its sheer size and the environments it typically inhabited in South America, often more humid than those dry caves, or permafrost regions, just didn't lend themselves to that kind of mummification. So while we don't have Megatherium's personal last meal on a fossilized plate, the incredibly detailed information gleaned from its relatives like Tachynothrotheriops provides a very strong analog. If its cousins with similar dental structures and body plans were consistently shown to be munching on a wide array of plants, it bolsters the case that Megatherium was doing the same, just on a much, much grander scale. Each leaf fragment, each seed identified from these rare internal archives, adds another brushstroke to the portrait of these animals as dedicated herbivores. It's tangible proof, something you can almost touch and see, transcending the inferences from bones alone. But our journey into the body of Megatherium, or at least into the scientific understanding of it, doesn't stop with what it ate last. There's another way to interrogate the long-dead method that delves into the very chemistry of their bones, asking them to reveal their dietary history, not just from one meal, but from a lifetime of meals. That thought of peering into an animal's very last meal preserved by some miracle of desiccation or freezing is truly tantalizing. It's about as direct as dietary evidence gets. But what if the animal wasn't mummified? What if all you have are its bones, those stony relics that have endured tens of thousands, even millions of years? Can mere bones tell tales of ancient appetites? You look at your colossal, shaggy Megatherium, its massive skeleton hidden beneath its thick hide and muscle, and you realize that yes, even those bones, those seemingly inert minerals hold a chemical diary of its life, a record of the foods that built and sustained its immense frame. Welcome then to the wonderfully clever world of stable isotope analysis. It sounds a bit like something out of a science fiction novel I know, using isotopes to figure out what a giant sloth had for dinner. But the basic principle is beautifully simple, summed up by the old adage, you are what you eat. Or to be a tad more precise for scientific pedants like myself, you're what you eat, assimilate, and don't entirely excrete, plus or minus a little biochemical tweak here and there. Essentially, the atoms that make up your food, the carbon, the nitrogen, the oxygen, and so on, are incorporated into your own tissues as you grow and live. And these atoms often come in slightly different versions or isotopes, some heavier, some lighter. The relative amounts of these heavy and light isotopes in your body tissues, particularly in your bones and teeth, which preserve so well, directly reflect the isotopic composition of the foods you've consumed over a long period. It's like your bones keep a secret diary of everything you've eaten. You muse, and paleontologists are just really nosy chemists who've learned to read it armed with very expensive machines. For reconstructing ancient diets, two elements are particularly chatty: carbon and nitrogen. Let's start with carbon. Carbon comes in a common form, carbon-12. Donondar, Pitin 12 Hasar Tolidor, and a slightly heavier, rarer stable isotope, carbon-13, Surinine, Sericones. Plants, through the magic of photosynthesis, absorb carbon dioxide from the atmosphere, but different types of plants do this in slightly different ways, leading to different ratios of Wurderschau 13 stars to Mauers or 12 $, in their tissues. We mainly talk about C3 plants and C4 plants. C3 plants, which include most trees, shrubs, and cool climate grasses, tend to discriminate more against the heavier Kuduwasan 13 and 9, so they have lower Kikuder 13 12 tolerant ratios. C4 plants, on the other hand, which include many warm climate or tropical grasses and some arid-adapted plants, are a bit less picky and end up with higher Mauriwacho Tidin Sunun 12 $, ratios. So by analyzing the carbon isotope ratio expressed as a Nasser delta, 13 in $30 value in an animal's bone collagen or tooth enamel, scientists can get a good idea of whether it was primarily eating C3 plants, C4 plants, or a mix. Basically, you think watching your Megatherium idly flick an ear, carbon isotopes can tell if our gentle giant preferred the leafy greens and shady forest snacks aisle or the sun-baked open grassland buffet section of the prehistoric supermarket. Then there's nitrogen, which usually comes as nitrogen-14, Wanaharm 14 $, and its heavier stable sibling, nitrogen-15, Canafornine Daraz. Nitrogen isotopes are fantastic for figuring out an animal's trophic level. That is its position in the food chain. Here's the neat trick: with each step up the food chain, tissues tend to become enriched in the heavier $15 isotope. So plants have a certain a delta sur $15 value. Herbivores that eat those plants will have delta 15 values that are typically 3 to 5 parts per mil higher than the plants. Carnivores that eat those herbivores will have delta 15 and minor values another 3 to 5 parts per mil higher still. Omnivores naturally fall somewhere in between, depending on how much plant versus animal matter they consume. Nitrogen isotopes help us figure out if an animal was a dedicated vegan. You summarize in your head a hardcore carnivore chowing down on said vegans, or just couldn't make up its mind and dabbled in a bit of everything. Like that one friend we all have who's flexitarian only on alternate Tuesdays when the wind blows from the west. The process itself involves taking a tiny, carefully cleaned sample of bone, often the dense collagen protein which preserves well, or tooth enamel. This sample is then combusted or chemically processed, and the resulting gases are fed into a machine called a mass spectrometer. You can imagine it as a very sophisticated, very expensive sorting device for atoms, precisely measuring the ratios of these different isotopes. The quiet hum of such a machine in a modern lab is a far cry from the rustling grasses of the Pleistocene around you, yet it connects these two worlds, translating ancient chemistry into dietary stories. The development and application of stable isotope analysis to ecological and paleontological questions was a legitimate historical event that truly revolutionized the field, really taking off from the 1970s and 1980s onwards. Pioneers like Michael De Niro and Samuel Epstein conducted foundational research demonstrating the systematic relationships between the isotopic compositions of an animal's diet and its tissues. Their work and that of many others who followed provided the crucial calibration and understanding needed to confidently apply these techniques to the fossil record, opening up whole new avenues for investigating ancient ecosystems. It's a quirky fact that different parts of your body, and indeed different components within your bones or teeth, can record your diet over different timescales. Bone collagen, for instance, turns over relatively slowly, so its isotopic signature reflects an average of your diet over several years. Tooth enamel, on the other hand, forms incrementally and doesn't remodel, so different parts of a tooth can record diet during the specific period that part of the enamel was forming. Scientists can even analyze the isotopes in your own hair. So if you suddenly developed an intense craving for, say, artisanal corn-fed chicken, and then switched to a purely seaweed-based diet after a life-changing coastal retreat, you think your growing hair might just snitch on your culinary adventures to a sufficiently curious chemist with a pair of scissors and a mass spec. Of course, interpreting isotopic data isn't always a simple connect-the-dots exercise. There's a whole field of academic debate around the potential complicating factors. The isotopic values of plants can be affected by things like water stress altitude or even the canopy effect in dense forests. The local isotopic baseline, what the plants and other animals in a specific ecosystem actually register, needs to be carefully established for accurate comparisons. And sometimes animals do weird things with their metabolism that can slightly alter the expected isotopic fractionations. But despite these complexities, stable isotope analysis provides an incredibly powerful tool, offering a quantitative window into the long-term dietary habits of creatures that have been extinct for millennia. It's a way of making the bones themselves speak of coaxing out secrets locked within their very atomic structure. And for a creature as enigmatic and massive as Megatherium, this chemical approach promised to add a whole new layer of understanding, potentially confirming or perhaps even challenging the long-held assumptions about its vegetarian lifestyle. The question was, what would those ancient atoms have to say? The idea of your bones silently chronicling your culinary life atom by atom is a rather profound one, isn't it? You glance at the Megatherium, still a picture of placid, shaggy monumentality on its sun-drenched rock. Its skeleton, a framework of truly epic proportions, is currently hidden from your view, but you can imagine those massive femurs, those broad ribs, each one a potential archive of dietary history, waiting for some future scientist with a very tiny drill and a very sophisticated machine. And when those pioneering isotopic studies finally turned their attention to the remains of Megatherium and its fellow giant ground sloths, the results that came back from the lab seemed to sing a clear, harmonious chorus one that perfectly matched the tune already being played by the teeth, claws, and inferred gut. The expectation based on everything that had been deduced from anatomy was straightforward. If Megatherium was indeed a dedicated herbivore, primarily browse on trees and shrubs, as Owen and others had proposed, its bone collagen should reflect that. Specifically, its carbon isotope signature, Dewanshorn delta 13 Title's values should fall squarely in the C3 plant range. Those trees, shrubs, and temperate flora, it shouldn't show much, if any, signal from C4 plants, which are more typical of open arid grasslands. And its nitrogen isotope signature, Tin delta 15 18 values should be relatively low, characteristic of an animal feeding at the base of the food web, a primary consumer of plants, not a consumer of other consumers. And lo and behold, as the early isotopic data started to trickle in during the latter part of the 20th century, particularly from the 1980s and 1990s, this is largely what the scientists found. Researchers building on the foundational isotopic principles we just discussed began applying these techniques more widely to fossil megafauna across the Americas. This application itself, this wave of isotopic investigation into extinct ecosystems, was a legitimate historical event in paleontology, like opening a new kind of window onto the past. When samples from Megatherium americanum, bones carefully extracted from museum collections across South America, were analyzed, their A delta 321 values consistently indicated a diet dominated by C3 vegetation. Our Megatherium was apparently quite the connoisseur of woodland buffets. You might quip, turning up its nose, or rather its entire giant head, at those trendy C4 grasses that some of the other grazers of the pampas might have been partial to. Similarly, its Dewanshorn delta 15 values were comfortably in the herbivore zone. There was no chemical hint of it regularly consuming other animals, which would have bumped those nitrogen values significantly higher. So the bones basically said, yep, salads. Lots and lots of salads. Occasionally a branch for dessert. You imagine the lab report concluding perhaps with a little flourish. No shocking revelations of secret midnight steak binges or clandestine fish suppers. The chemical data from the bones themselves seemed to confirm what the physical structure had long suggested. Megatherium was a browser, a leaf eater, a consumer of the forested and woodland environments of Pleistocene South America. It's amazing to think about the meticulous work involved. Picture a paleontologist or an archaeochemist in a clean lab, a stark contrast to the dusty dig sites or the primeval landscape you're currently inhabiting in your mind's eye. They'd be handling a fragment of a precious Megatherium bone, perhaps a piece of rib or a chip from a femur that's tens of thousands of years old. The process of drilling a tiny sample, usually just a few milligrams, of bone powder from such an irreplaceable fossil is done with extreme care. It's a quirky thought, but paleontologists treat these giant bones like the crown jewels. You reflect, so drilling into one, even for a minuscule sample for the mass spectrometer, probably feels like performing very delicate, very nerve-wracking keyhole surgery on a national treasure, all while hoping it doesn't suddenly crumble to dust or awaken a vengeful prehistoric spirit demanding to know why you're poking its femur. This convergence of evidence, the anatomical interpretation of teeth and claws pointing to herbivory, the logical inference of a large fermenting gut, and now the chemical signatures from the bones themselves, all telling the same story, was incredibly powerful. It felt like the case was pretty much closed. Megatherium was a C3 browser. Full stop. It's amazing what you can learn from a bit of bone dust in a machine that costs more than your house when you think. Suddenly a bone isn't just a bone. It's a dietary confession, a chemical fingerprint of meals long past. Of course, even within this strong consensus, there were still nuances for academic debate. For instance, while the C3 signal was clear, was it exclusively C3 plants from forests, or could it include C3 plants from more open woodlands or even riverside vegetation? And how did its isotopic signature compare to other contemporary herbivores in the same environments? Sometimes interpreting nitrogen values can get a bit tricky, as the baseline 200 delta 15 nitrogen in soils and plants can vary from place to place or be affected by factors like aridity, which can sometimes make a herbivore look a tiny bit higher on the food chain than it actually is. So while the main conclusion was herbivory, the exact dietary breadth and ecological niche within that herbivorous framework continued to be refined. Some studies might show slight variations depending on the geographical location or the specific geological age of the Megatherium sample, hinting at adaptations to local flora or subtle shifts in diet over time. But these were largely fine-tuning discussions. The main takeaway from these initial pioneering isotopic forays into the world of Megatherium was a resounding confirmation of its plant-eating lifestyle. It was as if the ancient bones themselves had spoken their atoms, whispering tales of leafy feasts and a life spent peacefully if ponderously munching their way through the Pleistocene. The science seemed solid, the picture complete. Megatherium, the gentle giant, the supersized salad enthusiast was a known quantity. And yet as you watched the great beast before you, its sheer scale and undeniable power still sending a little shiver down your spine, despite its current placidity, a tiny seed of doubt, or perhaps just curiosity, might begin to sprout. Is any creature, especially one so complex and successful for so long, ever that straightforward science, after all, has a delightful habit of revisiting closed cases when new evidence or new ways of looking at old evidence come to light? The story of Megatherium's diet, it would turn out, wasn't quite ready for its final chapter just yet. The isotopic signatures, those chemical whispers from deep time, seem to have painted a rather clear picture, haven't they? Your Megatherium, our colossal shaggy friend currently enjoying its prehistoric siesta, appears to have had its dietary preferences confirmed by the very atoms of its being a dedicated consumer of C3 plants, a browser of epic proportions. The science looks solid, the case files neatly stamped herbivore. And for a good long while, that was that. The gentle giant narrative supported by teeth claws as branch hooks inferred gut, and now bone chemistry was the accepted truth. It was a comfortable, tidy explanation for a magnificent, if rather unconventional beast. But science, has this wonderfully restless quality. It's like a toddler who, upon being told a story, immediately asks, but why? And then, but what if? No matter how settled a theory might seem, there are always curious minds poking at its edges, re-examining the evidence with fresh eyes or bringing new techniques to bear on old bones. And so slowly, almost imperceptibly, at first, a few gentle questions began to surface around the exclusively herbivorous lifestyle of Megatherium. These weren't dramatic headline-grabbing refutations, not yet, but more like the first few stray pebbles that precede a potential landslide of thought. One of the biggest, quite literally nagging questions revolved around its sheer, overwhelming size. You look at your Megatherium, 20 feet long, weighing perhaps 4, 5, even 6 tons. That is an immense amount of biological machinery to keep running. To maintain that physique on leaves alone, you can't help but ponder it would need a 24/7 all-you-can-eat salad bar, probably with its own dedicated Pleistocene delivery service, perhaps staffed by very fast, very nervous, smaller mammals. Leaves, while abundant in some environments, aren't always the most nutrient-dense or calorie-packed food source, especially when compared to, say, a nice juicy fruit or, well, something meatier. Could a diet solely of leaves and twigs consistently provide the colossal energy and protein budget required by such a giant, especially through seasonal variations in plant quality or availability? Some researchers began to wonder if there wasn't a missing piece in that energetic equation. Then there were those magnificent claws again. Yes, Owen's branch-pulling hypothesis was elegant and widely accepted. But you look at them, thick, curved, incredibly strong, and undeniably sharp. They certainly could hook branches. But were they perhaps a little over-engineered for just that task? Those claws weren't just for gently coaxing leaves from a tree. You think watching one idly twitch, they looked like they could open a bank vault or at least a very stubborn, very large clamshell if Megatherium had a sudden craving for seafood, which granted seems unlikely. Their formidable nature seemed to hint at capabilities beyond just arboreal salad acquisition. Defense against contemporary predators like Smilodon or giant short-faced bears, almost certainly. But could there be more? The metabolic rate of xenothrans that unique group Megatherium belongs to also threw a bit of a curveball. Modern sloths, armadillos, and anteaters generally have lower basal metabolic rates compared to other mammals of similar size. If Megatherium shared this trait, its overall energy needs might have been somewhat lower than you'd expect for such a behemoth, making exclusive herbivory more sustainable. However, accurately estimating the metabolic rate of an extinct animal is notoriously tricky. Was its metabolism truly low for its size, or did its gigantism come with its own unique energetic rules? This became, and in many ways still is, a point of open academic debate. If its metabolism wasn't that low, the protein and calorie demands would remain daunting for a pure leaf eater. You also have to consider the bustling competitive world it inhabited. The Pleistocene landscapes of South America were teeming with other large herbivores, gomphotheres, toxodonts, giant capybaras, herds of ancient horses and camelids. That's a lot of mouths vying for the available plant resources. Was the C3 browse always plentiful enough to support everyone, including the king-size appetite of Megatherium? Or might a little dietary flexibility and ability to capitalize on an occasional, easily accessible protein-rich windfall have offered a significant advantage in such a competitive environment? The very idea of questioning its strict herbivory was for a long time almost heretical. But slowly, as paleontological techniques advanced, more sophisticated biomechanical modeling, a deeper understanding of paleoecology, and the sheer accumulation of more fossils from more diverse sites, scientists began to reevaluate old assumptions. This wasn't a single aha moment or a dramatic historical event where someone found a Megatherium skeleton with a half-eaten steak. It was more a gradual shift, a growing unease with the perfect neatness of the gentle giant package. Researchers started to publish papers, perhaps tentatively at first posing these questions, exploring the what-ifs. It's a quirky thought, but imagine if Megatherium did occasionally supplement its diet. Given its immense size and presumed slowness, it wouldn't have been chasing down swift prey. It wouldn't be a cheetah, that's for sure, you chuckle. More like a heavily armed ambulatory compost heap that occasionally developed a craving for something a bit more substantial than a twig. If it did eat meat, it would almost certainly have to be scavenged carrion, or perhaps very small, very slow, or very helpless prey that it could simply overpower. Imagine its surprise, you muse, if it accidentally crunched on a particularly large, juicy beetle in its leafy mouthful. Extra protein. Not bad, not bad at all. Wonder if there are any more of these crunchy bits around here. It could be the start of a whole new culinary adventure. These emerging doubts didn't overthrow the herbivore model overnight. Not by a long shot. The anatomical evidence for plant eating was still incredibly strong. But these questions, these little chinks in the armor of the established theory, began to create an intellectual space. They opened the door just a crack, allowing for the possibility that Megatherium's dietary story might be a little more complex, a little more nuanced than a simple tale of leafy greens. The giant was still, by all primary accounts, a plant eater. But only a plant eater. All the time, under all circumstances. That was the question that started to hang ever so faintly in the prehistoric air. That faint, lingering question, the what if. Hanging in the prehistoric air around your colossal snoozing Megatherium began to coalesce into something a bit more tangible than just vague doubts. If a diet strictly of leaves and twigs presented certain energetic challenges, and if those impressive claws seemed a tad overqualified for mere branch pulling, then perhaps, just perhaps, its dietary habits weren't quite as rigidly vegetarian as everyone had assumed for so long. This is where the idea of Megatherium as an opportunistic omnivore starts to tentatively step onto the scientific stage, blinking a little in the bright light of established theory. Now, opportunistic omnivore doesn't mean you should suddenly picture your Megatherium as a 20-foot-tall clawed wolf actively stalking herds of prehistoric horses with a predatory glint in its eye. Not at all. The primary evidence still pointed overwhelmingly towards a plant-based diet. But opportunistic is the key word here. It suggests an animal that, while predominantly herbivorous, wouldn't necessarily turn up its nose, or its surprisingly small prehensile snout, at an easily acquired high-value non-plant food item if the chance arose. It's like your vegan friend who occasionally eats a bit of cheese when they think no one's looking. You muse, except this friend is 5 tons covered in shaggy fur and has claws that could redecorate your entire apartment without trying. Why would a creature so seemingly well adapted to browse leaves even consider such dietary deviations? Well, remember those immense energetic demands we talked about. Maintaining that sheer bulk required a constant, massive intake of calories and protein. While leaves are plentiful, their nutritional quality can vary dramatically with season and plant type. During lean times or in environments where high-quality browse was scarce or heavily competed for an occasional protein, and fat boost from another source could have been incredibly beneficial, a real evolutionary advantage. Think of it as a vital top-up to its regular leafy fare. And those formidable claws and powerful forelimbs, if Megatherium stumbled upon a carcass, say an animal that had died of natural causes or one killed by another predator, those same tools so adept at pulling down branches could also theoretically be pretty effective at tearing through tough hide to get at the meatier bits inside. Or they could have been used to defend such a scavenged prize from smaller, more agile competitors like dire wolves or even other less massive ground sloths. Why go to all the trouble of chasing down your food? You can almost hear a pragmatic Megatherium thinking, when someone else can do the hard work and you just show up fashionably late for the leftovers, work smarter, not harder, Pleistocene style. It's not an unheard of strategy in the animal kingdom. Many animals we typically consider strict herbivores have been documented occasionally consuming animal matter. Deer have been observed eating bird eggs or nestlings, presumably for a protein kick. Hippos, those riverine tanks, are known to scavenge carcasses from time to time. These aren't their primary food sources, not by a long shot, but they represent a flexibility and ability to take advantage of available resources. So the idea of a predominantly plant-eating Megatherium, occasionally indulging in a bit of found protein, wasn't entirely without precedent in the broader biological world. The formal suggestion of omnivory or significant scavenging in ground sloths, including potentially Megatherium, began to appear more explicitly in scientific papers and conference presentations in the later decades of the 20th century and into the 21st. This marked a subtle but important historical shift. It wasn't a sudden revolution, but a growing willingness among some paleontologists to propose and test hypotheses that went against the long-established grain. These ideas were often met with skepticism naturally as they challenged a deeply entrenched paradigm, but they were based on reevaluations of anatomy, ecological modeling, and those persistent questions about energetics. It's a quirky image, isn't it? Our slow-moving, seemingly placid giant, the epitome of gentle herbivory, perhaps delicately or more likely not so delicately, cracking open a clutch of giant bird eggs it stumbled upon or patiently ripping into a long-dead glyptodont. Probably not a dainty eater if it did try meat. You chuckle. More grab, gulp, and hope no one saw me deviate from my leafy greens commitment. The very thought of it brings a new dimension to the creature, a hint of a more complex, perhaps even slightly more cunning nature than its traditional portrayal allowed. Of course, this opened up a whole new arena for academic debate. If Megatherium was an opportunistic omnivore, how often did it indulge what specific non-plant items might it have targeted? Was its digestive system presumably so well adapted for fermenting plants, even capable of efficiently processing animal protein and fat in any significant quantity? Could its teeth, those ever-growing grinding columns, actually manage to shear or crush meat and bone effectively, even if only occasionally? These were all valid and challenging questions that the proponents of dietary flexibility had to address. The opportunistic omnivore theory was intriguing. It offered potential solutions to some existing puzzles, but it needed more than just circumstantial arguments. It needed evidence that Megatherium was not just willing, but also able to incorporate other foods into its diet. So while the foundation of herbivory remained strong, this new hypothesis added a fascinating layer of complexity. It suggested that Megatherium might have been a more adaptable, more versatile creature than previously imagined, a survivor that used all its impressive attributes to navigate the challenges of its Pleistocene world. The image of the simple, peaceful leaf eater was starting to blur at the edges, replaced by something potentially a little more resourceful. The next step, then, would be to look even closer at its anatomy, particularly its offensive and defensive equipment, those jaws and claws, to see if they really were up to the task of more than just processing plants. The idea of your Megatherium, that colossal shaggy browser, occasionally indulging in a non-vegetarian snack, is certainly a thought-provoker, isn't it? It adds a layer of unexpected complexity to this gentle giant. But for such opportunistic dietary expansion to be feasible, even sporadically, the creature would need the right equipment. It's not enough to just stumble upon a free meal. You need to be able to actually process it. And so your attention and that of a new generation of inquisitive paleontologists naturally turns to its formidable head, specifically its jaws and the power they could generate. Were they truly just for grinding leaves, or could they, in a pinch, handle something a bit more substantial? You look at the Megatherium's head, which in proportion to its vast body seems almost comically small, perched atop that thick, muscular neck. It has a relatively short snout, and its skull, while robust, doesn't immediately scream bone-crushing carnivore. The zygomatic arches, those cheekbones that anchor the powerful chewing muscles, are certainly well developed, indicating a good deal of masticatory might. But power for what exactly? Those ever-growing peg-like cheek teeth we discussed earlier were fantastic for pulverizing fibrous plants, their self-sharpening ridges making short work of tough leaves and twigs. But meat bone, that's a different culinary challenge altogether. This is where the fascinating field of biomechanics comes into play. Paleontologists can't unfortunately pop a dynamometer into a living Megatherium's mouth to measure its bite force directly. Slightly problematic that you muse, and probably wouldn't end well for the dynamometer or the paleontologist. Instead, they use the information preserved in the fossils, the size and shape of the bones, the inferred positions and sizes of the jaw muscles based on attachment scars on the skull, to build sophisticated models. These models, often aided by computer simulations like finite element analysis (FEA) in more recent times, can estimate the stresses and strains the skull could withstand and the forces the jaws could generate. The development and increasing sophistication of these biomechanical modeling techniques throughout the late 20th century, and really taking off in the 21st, was a legitimate historical event in paleontology, allowing researchers to quantitatively test hypotheses about how extinct animals function. So what did these studies begin to suggest about Megatherium's bite? Well, the estimates for its bite force are, as you might expect for such a large animal with strong jaw muscles, quite respectable. It might not have won any awards for most ferocious bite of the Pleistocene compared to specialized carnivores. You think, but it could probably still open a very stubborn jar of prehistoric pickles, or perhaps, with a bit of effort, a moderately sized glyptodont shell, if it found one already conveniently deceased. The power was certainly there for more than just gently bruising leaves. However, sheer force is only part of the equation. The tools that force is applied with are equally important, and here Megatherium's teeth presented a bit of a conundrum for any dedicated meat-eating scenario. As we've established, it lacked the sharp incisors for nipping the slicing carnassials of cats and dogs for shearing flesh, or the bone-splintering conical teeth of a hyena. Trying to eat a steak with those grinders, you chuckle to yourself, would be like trying to type a novel wearing oven mitts. Theoretically possible if you're desperate, but incredibly inefficient and undoubtedly messy. So even if the jaw muscles could generate a hefty chomp, the teeth themselves weren't optimized for processing large quantities of meat or breaking down major bones in the way a dedicated carnivore or scavenger would. This leads to an interesting area of academic debate. If Megatherium did scavenge, how did it go about it? Could it have used its overall brute strength and perhaps those massive forelimbs? We'll get back to those to dismember a carcass and then use its powerful but non-specialized bite to crush smaller bones or tear off manageable chunks of softer tissue. Some researchers have suggested that its bite might have been sufficient to break into carcasses or deal with smaller skeletal elements, especially if the prey was young or the bones already somewhat compromised. Others remain skeptical, arguing that the dental apparatus was so clearly geared for herbivory that any significant meat consumption would have been highly problematic and inefficient. The gape of its mouth also comes into question. How wide could it actually open? Its motto probably wasn't "say ah" for a dental checkup, You imagine. But more like stand back, this whole operation might get a bit wide if I'm trying. That compelling idea of a more resourceful Megatherium, a giant that might not have been a slave to its leafy diet, hangs in the quiet air around you. The theory of opportunistic omnivory is tantalizing, but it demands that the animal's toolkit be up to the task. Your gaze drifts back to those colossal forelimbs, currently resting placidly, but possessed of an undeniable latent power. And you focus once more on those claws, the magnificent curving implements at the end of each massive paw. We've considered them as gentle, albeit oversized hooks for pulling down branches. But looking at them again with a newfound sense of suspicion, you have to ask, is that all they were for? Let's revisit them not as gardening tools, but as potential weapons. Each forefoot bore three enormous sickle-shaped claws, with the central one being the largest and most formidable. The underlying bone core alone could be over a foot in length, and in life this would have been covered in a thick, hard sheath of keratin, just like the claws of a modern cat or bear, making them even longer, stronger, and sharper. We know this for a quirky fact because remarkably preserved mummies of other ground sloths like Neanothrotheriops, found in dry caves, have been discovered with these horny sheaths still intact over the bone. It gives us a much more vivid and frankly terrifying picture of their true living sharpness. It never had to worry about opening stubborn pickle jars, you think to yourself, or cars or bank vaults. Now consider the power behind those claws. You've already appreciated the massive musculature needed for pulling down tree branches. But that same system, powerful shoulder back and chest muscles, pulling on incredibly robust arm bones, could just as easily power a devastating swipe. Imagine your Megatherium reared up on its hind leg and tail tripod, a stable 20-foot-tall turret of power swinging one of those forelimbs. The speed might not have been lightning fast, but the sheer force, the momentum behind a multi-ton animal swinging an arm tipped with what are essentially three giant knives would have been apocalyptic. Their defensive use is almost beyond question. In a world populated by predators like the saber-toothed cat Smilodon and the giant short-faced bear, Arctodus, a Megatherium couldn't afford to be a helpless walking buffet no matter how large. A direct confrontation would be risky for any predator. Any Smilodon trying to sneak up on it, you muse, would be playing the most dangerous game of tag-your-it in history, where it means a rearranged collection of your internal organs. A single well-aimed swipe could have disemboweled or crippled even the most formidable aggressor. The claws were at the very least a powerful argument for leaving the giant sloth alone. But the more provocative question, the one that ties back to those emerging doubts about its diet, is whether these claws could have been used offensively. Not for chasing down gazelles, of course, but for acquiring meat in other ways. If a Megatherium stumbled upon a large carcass, say a deceased toxodon, would those claws be suitable for tearing through its thick hide to access the rich meat in and organs within? The force required would be immense, but one look at the sheer robusticity of its arms suggests it was more than capable. It would be the ultimate can opener for a glyptodon-sized can of whoop-ass, or lunch, as you morbidly jest. This is where modern science has provided some fascinating, if not entirely definitive insights. The advent of sophisticated biomechanical modeling, particularly a technique called finite element analysis (FEE), has been a major historical event in paleontology in recent decades. FEA is an engineering method used to calculate how structures respond to stress, and paleontologists have brilliantly co-opted it. They can create a detailed 3D digital model of a fossil bone, like a Megatherium claw, and then apply virtual forces to it to see where it's strong and where it might break. You could simulate the stress of hooking and pulling a branch, and then compare that to the stress of slashing into soft tissue, or even the high-impact shock of striking something hard like bone. The results of such analyses and the interpretations thereof are a major source of ongoing academic debate. Were the claws structurally robust enough to withstand the violent, unpredictable forces of combat, or butchering a carcass? Some researchers argue that the claws, while strong in a pulling motion as required for herbivory, might have been too laterally compressed or brittle to handle the twisting or impact forces of a struggle. A broken claw, much like a broken saber tooth for Smilodon, could be a serious life-threatening problem. Others argue that their structure was more than adequate for slashing into the soft underbelly of another large animal or tearing apart thick muscle as long as it avoided heavy bone impact. The debate hinges on these fine interpretations of biomechanical limits. So you're left with a fascinating duality. These claws were unquestionably brilliant tools for a life of high brows fitting perfectly into the peaceful herbivore model. Yet they simultaneously seem to be terrifyingly effective weapons, either for defense or for a more grisly, opportunistic offense. It's like discovering your gentle vegetarian gardener also happens to own a full set of military-grade combat knives. You start to wonder if you really know them at all. This reevaluation of the claws is crucial. It changes the very character of the animal in your mind. It shifts from being a passive defensive giant into something far more formidable, a creature capable of inflicting incredible damage if it so chose. It adds a layer of menace, a sharp cutting edge to the soft, shaggy outline. The peaceful giant now seems a little less peaceful, its quiet repose on that rock now imbued with a sense of immense coiled power. The question is no longer just, could it have eaten meat, but also, did it have the necessary weapons to acquire it? And a long, hard look at those spectacular claws suggests that the answer to the second question might very well be yes. Those colossal claws, you now realize, weren't just for gently pruning the Pleistocene's loftiest branches, nor solely for a dramatic talk to the hand, a very, very large sharp hand defense against a marauding Smilodon. If we're entertaining the notion that your shaggy 20-foot companion might have occasionally partaken in non-botanical fare, then those formidable armaments open up a rather intriguing, if slightly grisly possibility scavenging. The idea of Megatherium, the great beast as a colossal, opportunistic corpse cleaner, is one that began to gain traction as scientists looked for ways to explain those nagging energetic questions and the sheer, almost over-the-top power of its physique. Why would an animal seemingly built for browse even bother with something as déclassé as a week-old carcass? Well, for one, carrion is essentially a free lunch packed with protein and fat. For an animal with the immense caloric needs of a megatherium, stumbling upon a recently deceased glyptodont or a toxodon that had succumbed to injury or illness would be like hitting the nutritional jackpot. It could probably smell a week-old bison buffet from miles away. You speculate imagining its large nasal cavity wasn't just for sniffing out the choicest leaves. Its nose was less subtle floral bouquet and more long-range carrion detection system, tuned to the delicate aroma of eau de expired armadillo. This keen sense of smell, common in many scavengers, would be vital for locating these scattered, unpredictable protein parcels. And once it found such a bounty, who was going to argue? Imagine the scene: a pack of dire wolves, perhaps, or a few opportunistic Ice Age vultures tentatively picking at a kill. Then over the horizon lumbers your Megatherium, a walking mountain casting a very large shadow. Imagine a pack of dire wolves, all excited about their find, you muse, and then this 6-ton clawed behemoth shuffles over. "Excuse me, gentlemen." It might as well be roaring. "I believe you're sitting on my lunch." Most would probably just hand over their metaphorical lunch money and apologize for the inconvenience. Its sheer size, combined with those terrifying claws we've just been admiring, would make it an apex scavenger capable of displacing almost any other predator from a carcass. It wouldn't need to be fast. It would just need to be there, an immovable, intimidating object with very persuasive natural cutlery. The actual process of scavenging would also play to its strengths. While its teeth, those ever-growing grinding columns we discussed, weren't designed for slicing meat or crushing large bones like a hyena's, those powerful forelimbs and claws certainly could have been used to rip open tough hides, tear apart muscle masses, and expose softer tissues and organs. It might not have been a neat or tidy eater. More of a face first into the buffet and don't come up for air until you hit something inedible kind of diner. You imagine a sort of all-you-can-eat horror movie for any smaller critters still hoping for a tiny scrap. The serious consideration of scavenging as a significant ecological strategy for many large prehistoric animals, not just the obligate carnivores, represents a notable shift in paleontological thinking that gained momentum in the late 20th and early 21st centuries. This broader scientific trend, a legitimate historical development in paleoecology, encouraged researchers to look beyond simple predator-prey dichotomies and consider the complex web of interactions that included opportunistic feeding on carrion. While direct fossil evidence of Megatherium, specifically scavenging, like finding its unique tooth marks on bones that also show carnivore tooth marks, is difficult to come by due to the nature of its dentition grinding, doesn't leave the same distinct scores as slicing or puncturing, the ecological logic began to seem more compelling. Of course, the extent and importance of scavenging in Megatherium's diet remains a hot topic of academic debate. Was it a regular, crucial supplement to its plant-based fare, something it actively sought out? Or was it a very rare, better-than-nothing occurrence when preferred vegetation was exceptionally scarce? Could it reliably locate and secure carcasses before they were too far gone or entirely consumed by more specialized scavengers? And how did it stack up against other powerful carrion consumers, like the giant short-faced bear? Arctodus simus, which was itself a formidable contender at any kill site. These questions are still being teased out from the fossil record and through ecological modeling. It's a quirky thought, but if Megatherium was a regular scavenger, its internal microbial zoo, so well adapted for fermenting tough plants, might have faced some interesting challenges when presented with a sudden influx of meat. Or perhaps it had a gut versatile enough to handle both, a testament to Xenarthran adaptability. One also wonders about the freshness preferences. Was it a connoisseur of the recently deceased, or would it tackle something a bit more well-aged? The details, alas, are lost to the mists of time, or perhaps locked away in some yet undiscovered chemical signature. But the scavenging hypothesis does provide a rather neat solution to some of the puzzles. It offers a way for Megatherium to acquire high-quality nutrients with relatively low energy expenditure once the carcass was found and secured, of course. It utilizes those powerful clawed forelimbs for a purpose beyond just wrestling with trees, and it paints a picture of a more adaptable, more resilient animal, one that could exploit a wider range of resources in its challenging Pleistocene environment. The image of the purely peaceful leaf-munching giant begins to acquire a slightly more rugged, opportunistic edge. It's still primarily a herbivore in this model, but one with a decidedly pragmatic and occasionally carnivorous streak. This idea that Megatherium might have actively sought out and consumed dead animals is a significant step away from the traditional view. It makes the creature more complex, more integrated into the full spectrum of its ecosystem's food web. And it naturally leads to an even more audacious, more controversial question: if it was willing to eat animals that were already dead, and it possessed such formidable weaponry, could it have just possibly sometimes taken matters into its own claws? That image of your Megatherium, this seemingly placid giant, occasionally indulging in a spot of scavenging, is certainly a compelling one. It adds a gritty, pragmatic layer to its otherwise serene, leaf-munching persona. But if it was going to supplement its diet with carrion, how would it fit into the rough-and-tumble world of Pleistocene scavengers? It wouldn't just be ambling up to an abandoned meal with a polite, "Excuse me, is anyone eating this?" It would be entering an arena already populated by highly efficient, often very aggressive specialists. To succeed, Megatherium would need to carve out its own particular niche, its own unique way of being a part-time corpse consumer. Given its sheer overwhelming size and those formidable claws we've discussed, its primary role in any scavenger guild would almost certainly be that of a dominant player. It wasn't so much joining the dinner party, you imagine, as the dinner party is now officially over for everyone else, and I'm taking all the dip and the bowls and possibly the table. Any smaller scavengers, packs of dire wolves, perhaps the fearsome Smilodon, if it was a lone individual or a small group, or even those giant, terrifying Teratorn birds, would likely give a very wide berth when a 6-ton Megatherium decided a particular carcass was its own. Its arrival would be a game changer, a signal for lesser beings to quickly develop an intense interest in the distant scenery, or perhaps take up competitive cloud watching as a new, less confrontational hobby. What kind of carcasses might it have targeted? Given its bulk, it might have been particularly effective at exploiting very large megafauna remains. a deceased gompho there, a toppled toxodon, or even another giant ground sloth. These massive packages of protein and fat might be too much for smaller predators to consume quickly or defend effectively. Megatherium, with its ability to tear into thick hides and its sheer staying power, could have monopolized such a bounty for days. It's even possible it played the role of a carcass opener. Imagine a giant herbivore with an incredibly thick hide, something that smaller carnivores struggle to breach. A megatherium with its immense strength and those powerful claws could potentially rip it open, not only feeding itself but also inadvertently creating access for smaller, less powerful scavengers once it had had its fill or moved on. A sort of ecosystem engineer, but for the recently deceased. Its scavenging technique, however, wouldn't have been one of delicate precision. Remember, its teeth were those of a grinder, not a slicer or a bone crusher. Unlike hyenas, it couldn't pulverize large bones to get at the marrow. Its style would be more about tearing off great hunks of muscle and soft tissue, gorging on what was accessible. Not a delicate surgeon meticulously dissecting the leftovers. You think more like a demolition crew on a lunch break. Table manners were probably not its strong suit. The aftermath of a Megatherium scavenging event on a large carcass might have looked rather dramatic. Bones scattered, the ground churned up from its immense weight, a scene of chaotic consumption. It's a quirky, if slightly unsettling thought that if Megatherium specialized in particularly ripe carcasses, its approach might have been heralded by an impressive, almost visible aura of decay and a truly awe-inspiring cloud of attendant blowflies. A walking, shaggy biohazard sign. The study of these ancient food webs, particularly the interactions within carnivore and scavenger guilds, became a much more sophisticated field in paleoecology during the late 20th and early 21st centuries. This focus on guilds, groups of species that exploit similar resources in a similar way, is a legitimate historical development in the science. Paleontologists began to meticulously map out who was eating whom, who was competing with whom, and who was cleaning up the leftovers in these Pleistocene ecosystems. They'd analyze tooth marks on bones from kill sites, look at the relative abundance of different predator and scavenger fossils, and try to build a picture of the hierarchy. Placing Megatherium into this hierarchy as a potential major scavenger was a fascinating exercise, prompting a lot of discussion. And naturally, there's plenty of room for academic debate here. How frequently would a slow-moving Megatherium actually encounter suitable carcasses before they were either too decomposed or entirely consumed by more fleet-footed scavengers like wolves or large predatory birds? Could it truly outcompete a determined pack of dire wolves or a giant short-faced bear at every kill? The short-faced bear. Arctodus simus was itself a colossal animal often suggested to be a formidable scavenger or kleptoparasite, an animal that steals kills from other predators. A standoff between a Megatherium and an Arctodus over a prize carcass would have been a truly epic confrontation, a battle of titans that would make any pay-per-view fight look like a minor squabble. The lack of distinct Megatherium tooth marks on bones due to their grinding nature makes it hard to find smoking gun evidence of its scavenging behavior, unlike the clear punctures and scores left by typical carnivore teeth. So was it a regular, strategically important part of its diet, or just a very occasional, better-than-starving windfall? Could it rely on finding enough carrion to make a real difference to its energy budget, especially given that it was likely not a particularly speedy traveler, making a wide search pattern potentially costly? These are the questions that researchers continue to grapple with, using ecological models, isotopic studies from more diverse tissues if possible, and careful re-examination of fossil sites. But the idea that Megatherium could have, and perhaps regularly did, muscle its way onto carcass sites using its size and weaponry to claim a share of the spoils adds another fascinating wrinkle to its character. It transforms it from a simple, peaceful browser into a more complex ecological player. Still predominantly a herbivore, yes, but one with a keen eye for an easy, if somewhat gruesome, opportunity. A pragmatic giant not above getting its claws dirty quite literally for a high-protein meal. It's a compelling image, this shaggy mountain of an animal patiently surveying its domain, not just for the greenest leaves, but also for the telltale signs of death, ready to assert its claim. And it leads you inevitably to a more unsettling thought. If it was so good at taking over a kill, so well equipped to tear into a carcass, and so clearly possessed of immense power, did it always wait for things to be conveniently dead already? That final question hangs in the cool Pleistocene air, heavy and unsettling. If your Megatherium had the power and the weaponry to dominate a carcass, did it always need to wait for nature or another predator to do the killing for it? You look at the creature, this immense shaggy beast, and try to square its placid demeanor with a more sinister capability. The idea of it as a scavenger was a big enough leap from the gentle giant model. But what comes next is a plunge into a far more radical, far more controversial abyss of speculation. This is where we introduce the most shocking theory of all Megatherium, the killer. Megatherium, the active predator. Let's be clear, this is not a universally accepted theory. In fact, it's one of the most hotly debated ideas in all of paleontology, a notion that sends ripples through the scientific community to this day. When this idea first came out, you can just imagine some paleontologists probably choked on their coffee and checked the date to make sure it wasn't April Fool's Day. A predatory sloth. What's next? Carnivorous rabbits, flying pigs. But as audacious as it sounds, the hypothesis was put forward with serious intent, backed by what its proponents believed was compelling, if circumstantial, fossil evidence. The theory doesn't envision Megatherium as a pursuit predator, a giant, shaggy cheetah. That would be absurd. Its body was built for power, not for speed. No, if Megatherium hunted, it would have been a specialist, an ambush predator, employing a strategy that leveraged its unique and formidable strengths. The proposed tactic is as bizarre as it is brutal. Find a slow-moving, heavily armored animal, use your immense weight and strength to push it over or incapacitate it, and then use those devastating claws to attack the soft, vulnerable underbelly. Its hunting strategy, you think grimly, wasn't speed. It was, I'm much, much bigger than you. You can't run away very fast, and I'm going to tip you over like a mischievous teenager tipping a cow, except with a significantly more permanent conclusion. And who would be the target of such a strange and terrifying hunting style? The prime candidate, according to the theory's proponents, was another icon of the South American Pleistocene, the glyptodont. Picture a glyptodont. It's essentially a giant armored mammal related to modern armadillos, but one that could be the size of a small car covered in a solid dome-like shell of bony plates. They were walking fortresses well protected from attack from above, but slow-moving. If you could somehow flip one onto its back, it would be as helpless as a turtle, in the same predicament, its soft underside completely exposed. And what creature in its environment had the sheer bulk and strength to do the flipping? Well, your friend on the rock over there certainly fits the bill. The idea of a sloth, the modern symbol of all that is slow, sleepy, and herbivorous, being a potential killer of giant armored tanks, is a quirky fact of paleontological theory in itself. It completely inverts our expectations. This theory, you muse, basically turns our shaggy leaf-eating hippie into a terrifying heavyweight MMA fighter, specializing in armored opponents. That's quite the career change. This shocking hypothesis was most famously and formally put forward in the mid-1990s. In a legitimate historical event that sent shockwaves through the paleontological world, the Uruguayan paleontologist Richard Farina, along with his colleague R.E. Blanco, published a paper titled Megatherium the Stabber. They argued that the anatomy of Megatherium, particularly its powerful forelimbs and the biomechanics of its claws, was well suited for this exact kind of predation. They proposed that it could deliver powerful stabbing blows with its claws, puncturing the soft tissues of an overturned glyptodont. The theory suggested that Megatherium wasn't just an opportunistic scavenger, but a kleptoparasite that stole life itself, not just leftover kills. Of course, this radical reimagining of Megatherium as a killer sloth ignited a firestorm of academic debate that still smolders today. Many paleontologists remained and still remain highly skeptical. They point to the teeth, which are still fundamentally the teeth of a herbivore ill-suited for slicing meat. They question the biomechanical feasibility, arguing those claws might not withstand the stresses of such a violent attack. They point to the animal's likely slow metabolism and the vast body of isotopic evidence that consistently points towards a diet of plants. The debate becomes a clash of interpretations. Are the claws and strength simply adaptations for highbrows in defense as traditionally thought, or are they evidence of a secret, gruesome, predatory life? You try to picture it, the scene playing out in your mind's eye. The slow, deliberate approach. The earth-shaking confrontation as tons of sloth muscle meet tons of armored glyptodont defense. The massive heave, the tipping of the living fortress, and then the final, brutal application of those scythe-like claws. It's a chilling vision, completely at odds with the placid creature you've been observing. It forces you to reconsider everything, to look at that immense power, not as a passive quality, but as a weapon that could be actively, ruthlessly deployed. The predatory sloth theory, whether ultimately proven right or wrong, is a powerful example of how science progresses. It challenges us to look beyond our preconceptions, to test every assumption, and to imagine possibilities that seem at first glance utterly outlandish. It forces the scientific community to re-scrutinize every bone, every muscle attachment point, every fossil site in search of evidence that will either support or refute the audacious claim. And in the case of Farina's hypothesis, it wasn't just a wild idea. He believed he had a very specific fossil site, a prehistoric crime scene that held the smoking gun. That audacious theory, Megatherium, the Glyptodon slayer, wasn't just pulled out of thin air, you understand. It wasn't merely a flight of fancy based on, wouldn't it be cool if... No, Richard Farina and his colleagues believed they had found a specific place, a particular assemblage of fossils, that told a rather grim and astonishing story. This wasn't just speculation about what could have happened. They pointed to a location in Uruguay, the Arroyo del Vizcaíno site near the town of Sauce, as a kind of prehistoric crime scene, where the evidence, they argued, pointed directly to Megatherium as a killer. Imagine yourself now transported not just to the Pleistocene, but to this specific, somewhat eerie location, as it might have appeared around 28,000 to 30,000 years ago, or perhaps as it appeared to the paleontologists who first began to unearth its secrets in the late 1990s. The Arroyo del Vizcaíno site is a paleontological treasure trove, a rich deposit of late Pleistocene megafauna fossils. The discovery and subsequent ongoing excavation and study of this site, largely spearheaded by Farina and his team, became a legitimate historical event in South American paleontology, precisely because of the controversial interpretations it generated. It's a place where the bones don't just whisper. According to some, they scream a tale of ancient violence. What Farina and his team reported from Arroyo del Vizcaíno was an unusual concentration of giant ground sloth, Megatherium americanum. Remains in very close association with an even larger number of glyptodon skeletons, primarily those walking tanks, Didicurus and Glyptodon. This close association in itself isn't necessarily proof of predation, but it was the starting point. Then came the more specific and far more contentious observations. They noted an unusual mortality pattern among the glyptodons. Often in natural accumulations or attritional death sites, you find a higher proportion of very young or very old individuals, those most vulnerable to disease, starvation, or less specialized predation. But at Arroyo del Vizcaíno, Farina reported a significant number of prime adult glyptodonts among the dead, suggesting that something other than natural causes or typical predation by smaller carnivores was at play. But the real smoking gun in their view lay in the alleged marks on the glyptodont remains. Farina and his colleagues described peculiar damage on some of the glyptodont carapaces, particularly on the underside and on bones of the pelvic girdle. These weren't the typical puncture marks of a smilodon's saber teeth, nor the gnawing patterns of wolves. Instead, they described what they interpreted as deep groove scratches and puncture-like wounds that seemed consistent in size and shape with the massive pointed claws of a Megatherium. The hypothesis was that a Megatherium would use its immense strength to topple a glyptodont. No mean feat, given these armored beasts weighed a ton or more themselves. And then with the helpless animal on its back, it would use those formidable four-limb claws to stab and tear at the vulnerable, unarmored underbelly, inflicting fatal wounds. The marks found on the bones, they argued, were the traces of this grisly, butchering or killing process. It's like CSI Pleistocene. You reflect, but the DNA evidence is a bit on the degraded side, and all the eyewitnesses have been dead for 30 millennia, leaving only their very battered remains as testimony. Furthermore, they argued that the site lacked an abundance of telltale signs from other large-known carnivores of the region. If these glyptodonts had been killed and consumed by, say, packs of dire wolves or a smilodon, one might expect to see characteristic tooth marks, different kinds of bone breakage, or a different pattern of disarticulation. The specific nature of the damage and the close association with Megatherium fossils led Fariña to finger the giant sloth as the primary culprit. It's a quirky, almost cinematic image, paleontologists working meticulously at this Uruguayan site, less like fossil collectors and more like forensic investigators at a very, very cold case. You can picture them, brushes and trowels in hand, carefully exposing a massive glyptodont carapace, then leaning in close, perhaps with hand lenses, searching for those crucial, telltale scratches or punctures that might betray its killer. One paleontologist sees a clear, deep claw mark from a 6-ton killer sloth. You muse, while another looking at the same mark might see where a particularly pointy rock was pressed into the bone by overlying sediments for 10,000 years, or perhaps damage from trampling by other heavy beasts after death. It's all in the eye and the interpretive framework of the boneholder. And this precisely is where the fierce academic debate ignites. While Fariña's team presented a compelling narrative, many other paleontologists remained unconvinced by their interpretation of the Arroyo del Vizcaíno evidence. Skeptics offered alternative explanations for the fossil assemblage and the marks on the bones. Could the site simply be a natural trap, perhaps a boggy area, or a drought refuge around a diminishing water source where many animals congregated and ultimately perished, their bones becoming jumbled together over time by water action or trampling? This is a common taphonomic scenario. Taphonomy being the study of everything that happens to an organism after it dies until it's discovered as a fossil. The interpretation of the claw marks is particularly contentious. Are they truly the work of Megatherium, or could they be the result of non-predatory processes? Bones can be scratched by being dragged over rough sediment, fractured by the pressure of overlying earth, or even marked by the roots of plants growing through them. Distinguishing these from genuine tool marks or predator marks made on fresh bone is an incredibly challenging task, often relying on subtle microscopic details and comparisons with experimentally produced marks. Being a glyptodont back then must have been quite stressful. You can't help but think. Not only do you look like a giant, mobile, extremely well-armored pebble, but now there's a serious scientific theory suggesting that a 6-ton sloth wanted to use you as a heavily fortified piñata, aiming for the soft, chewy center. So the Arroyo del Vizcaíno site, far from being a closed case, became the epicenter of the killer sloth debate. It's a place where the evidence itself is complex, and its interpretation is viewed through very different theoretical lenses. For Fariña and his supporters, it's a prehistoric Pompeii of predation. For skeptics, it's a fascinating, but perhaps more mundane accumulation of fossils whose unusual features can be explained by less dramatic, more conventional geological and biological processes. The truth, as is often the case in paleontology, is likely buried under layers of sediment, time, and ongoing scientific argument. The image of that prehistoric crime scene at Arroyo del Vizcaíno is a powerful one, isn't it? A jumble of ancient bones that seems to tell a story of a giant sloth turned super predator. It's the kind of theory that captures the imagination, a dramatic twist in the tale of a creature everyone thought they had figured out. But in the world of science, every dramatic accusation needs to be cross-examined, and the case for Megatherium, the killer, was immediately met with a host of skeptical yet equally scientific rebuttals. For every paleontologist who saw a predator's signature at the site, another saw the confusing, chaotic handiwork of time itself. The primary line of defense for the traditional herbivorous Megatherium comes from a field of study you've heard mentioned before, taphonomy, that wonderful science of everything that happens between death and discovery. Basically, you reflect the taphonomy argument is the paleontology equivalent of saying, "No, Your Honor, it wasn't murder. The victim just tripped and fell onto a dozen knives repeatedly over the course of several thousand years while being gently rearranged by a river." It's a bit more complicated than that, but you get the gist. Skeptics argue that the entire Arroyo del Vizcaíno assemblage can be explained by natural processes without needing to invoke a slow-motion sloth assassin. They point out that the site is, after all, an ancient river channel. It's entirely possible that it acted as a natural trap during a drought, drawing animals to a dwindling water source where they weakened and died, or carcasses from miles upstream could have been washed down during floods concentrating in this one location. Such a scenario would naturally jumble the bones of different species like Megatherium and Glyptodonts, creating the illusion of a direct interaction where none existed. The unusual mortality pattern of prime adults. A severe drought or a sudden flood can be indiscriminate, killing animals in their prime just as easily as the old and the sick. And what about those supposed claw marks? The smoking gun of the predation theory. Taphonomists are quick to point out a plethora of other potential culprits. Imagine the scene after these animals died. Their bones lying in the mud could have been trampled by other massive megafauna, also using the water source. A multi-ton gompha there, stepping on a glyptodont carapace, could easily create fractures and deep scores that might 30,000 years later look deceptively like tool marks. The simple immense pressure of tens or hundreds of feet of sediment piling up over the millennia can warp, crack, and score bones. Even the slow, patient grinding of sand and gravel in a river current can abrade bones in ways that mimic butchery marks. The scientific debate over the origin of bone surface modifications is a legitimate historical constant in paleontology, with researchers presenting detailed analyses at conferences and in papers showing how natural processes can create marks virtually indistinguishable from those made by predators or even human tools. There have been entire conference sessions dedicated to meticulously picking apart the evidence from sites like this. Then there are the anatomical counterarguments, many of which circle back to what we've already discussed. The biggest sticking point for many remains the teeth. Even if a Megatherium successfully killed a glyptodont, you reason it would have had a terrible time actually eating it. It's like being handed a beautifully cooked steak and being told to eat it with 2 wooden spoons. You might manage to get some of it down, but it's going to be messy, deeply unsatisfying, and you'll leave most of it behind. Its teeth were grinding mills, not meat shears. Proponents of the theory argue it could have just slurped up the soft organs and blood, but this seems an inefficient payoff for the immense risk and effort of tackling a 1-ton armored beast. The claws, too, come under renewed scrutiny in this debate. While undeniably powerful, were they really suited for the dynamic chaos of a death struggle? The biomechanical arguments cut both ways. Skeptics maintain they were optimized for the sustained, powerful pulling motion needed for browse, and that the kind of impact or twisting forces involved in a life-or-death battle might have risked catastrophic failure, a snapped claw that would be a death sentence. And finally, there's the deafening silence from the isotopic evidence. All those chemical diaries locked in the bones of Megatherium after Megatherium consistently scream plant eater. While very occasional opportunistic scavenging might be hard to detect a regular predatory strategy, one specialized enough to target giant armored glyptodonts should, many argue, leave some kind of detectable shift in the nitrogen isotope values. The fact that it doesn't is, for many researchers, the most powerful piece of evidence against the predation hypothesis. It suggests that whatever was happening at Arroyo del Vizcaíno, it wasn't part of Megatherium's regular meal plan. The back and forth on this topic can be passionate and has persisted for years. It's a quirky fact of scientific life that some of these debates can take on a life of their own, becoming almost legendary feuds. You get the feeling, you think with a smile, that some of these paleontologists will be arguing about the Arroyo del Vizcaíno site until they themselves are fossils, and future scientists will